Welcome mathematicians. In today's video we'll be looking at conditional probability. You have the equation in front of you at the moment. It shows you that the probability of event A given event B, and this is what the line represents, given the event B, is equal to the probability of A and B divided by the probability of event B. So in this video we'll be looking at three different scenarios. One is visual examples. The second is where we'll look at Venn diagrams, and the third is where we look at two-way tables. Consider all the possible outcomes when throwing two fair six-sided dice. So in this scenario, we've got one white dice, which is represented by the white square, and one blue dice, which we have as our blues. You can see here that there are six possible numbers that can be thrown for the whites. So you can throw 1, 2, 3, 4, 5, 6. And of course, there's six possible numbers that can be thrown by the blue die, 1, 2, 3, 4, 5, 6. So in total, we have 36 possible outcomes. So as a starting point, what is the probability of throwing a pair of ones? Well, as you can see, it's a 1. This is the successful outcome. There's 1 out of 36 possible outcomes. So the probability of throwing a pair of ones is 1 out of 36. Now let's look at some conditional statements. Again, what's the probability of throwing a pair of ones? However, in this situation, we're stating that given the blue die is a 1. So here we've got 36 possibilities, but if we state that the blue die has to be a 1, then suddenly we're reduced to only 6 options. And now the successful outcome of throwing a pair of ones when the blue die is a 1 is only 1 in 6 probability. Conditional statement number 2. What's the probability of a white die being even given the blue die is a multiple of 3? Well, here's the blue die with multiples of 3. Whether blue die is 3 or 6, they're multiples of 3. And the probability that the white die is even in this situation, well, there's a 2 for the white, another 2, a 4, and 6s. So we have here 12 possible outcomes with 6 successful outcomes. So 6 out of 12 gives us a probability of 1/2, 1 over 2. Our third conditional statement is the reverse. Let's consider the probability of the blue die is a multiple of 3 given the white die is even. Now we've just reversed these two statements. Does that make a difference? Previously, if we go back, it was a 1 in 2 probability. Let's look now with the reverse. Blue die is a multiple of 3 given the white die is even. So first of all, let's remove all the white dies are odd, and here's our white dies are even. So we've got 2s, 4s, and 6s. Now we're looking for the blue die as a multiple of 3. So there's 1, 3, and a 6, 3 and a 6, 3 and a 6. So now we have 18 possible outcomes with 6 successful outcomes. So 6 out of 18 is 1/3. Now that is different to the half that we had before when these two conditions were reversed. So these are conditional statements looking at visual examples. Let's now look at a Venn diagram. So our new scenario, a 10-sided die with faces number 1 to 10 is rolled. So this is what a 10-sided die looks like. I wouldn't mind one of those. Bit of a novel looking object. So event A, the number rolled is less than 7. And event B, the number rolled is a multiple of 3. So task 1 is to construct a Venn diagram to represent this information. So here's the numbers 1 to 10 available on this die. Event A is where the numbers rolled is less than 7. So we've got a 1, 2, 3, 4, 5, and 6. So we can place all those numbers in event A. Event B, the number rolled is a multiple of 3. So there's a 3. There's a 3 goes into 6 as well, and 3 goes into 9. These are the 3 numbers that are a multiple of 3 up to the number 10. And you can see that number 3 and 6 are both in set A and set B. So they go in this little intersection section between event A and event B with overlap. And number 9 is only in event B, set B by itself. It does not occur in event or set A because it is a number that's greater than 7. Now finally, we also have numbers 7, 8, and 10. They needed to be added to our space as well. So 7, 8, and 10 are not part of set A, not part of set B, but they are part of the possible numbers being thrown on a 10-sided dice. So here we have our Venn diagram to represent this information. From that, let's now perform the following tasks. So task number 2, calculate the probability that the number rolled is less than 7 given it is a multiple of 3. So this is our conditional statement, given it is a multiple of 3. So to calculate this mathematically, the probability of event A given B, we have to look at what are the number of outcomes in both A and B divided by the number of outcomes on this given event B. So first of all, the probability of A given B, the number of outcomes in event A and B. A and B where they overlap, there's 1, 2, number 3 and 6, there's 2 possible outcomes. And in total in B, there's 1, 2, 3 outcomes. So the probability of the number rolled is less than 7, given it's a multiple of 3, is 2 out of 3. Less than 7 and a multiple of 3 is 2 out of 3. Task number 3. Let's try the reverse. Calculate the probability the number rolled is a multiple of 3, given it is less than 7. So this is the reverse arrangement. So we want the probability of event B given event A. To calculate the number of elements in set B and A and the total number in A. The number of outcomes in B and A is this section in the middle. The overlap is numbers 3 and 6. There's 2 divided by the number of outcomes in set A, which is this collective region of 6. So the probability of the number rolled is a multiple of 3, given that it is less than 7, is 2 on 6 or 1/3. And that can be represented. Here's our events of numbers rolled is a multiple of 3, given that it's less than 7. It's 2 out of a possible of 6, or 1/3 is the probability. Finally, let's have a look at two-way tables. So have a scenario here. In a particular class, 55% of the class are girls. It is also known that 60% of the boys love mathematics, while only 35% of the girls love mathematics. Now we know this is not true. We know that 100% of boys and girls all love mathematics. But let's go with this example. Task 1, construct a two-way table to display this information. So I've already got a 1 here because we know that all the numbers in the bottom row and the right-hand column have to add up to 1 when we look at probabilities. That's the total probability of 1. So first of all, 55% of the class are girls. So as a decimal, that represents 0.55. Girls, total of girls is 0.55. Now we've got 55% of the class are girls. That leaves us with 45% of the class are boys, so 0.45. Now we're advised that 60% of the boys love mathematics. So of the 45% of the entire class, 60% of the 45% are boys that love mathematics. That leaves us with 27% or 0.27 as a decimal. So 27% of the entire class are boys that love mathematics. Which means if we've got 60% of the boys love mathematics, that leaves us with 40% of the boys that don't love mathematics. So 0.4 of the total of 0.45, so 40% of the 45% of the class, which are boys, don't love mathematics, gives us a value of 0.18 or 18%. So 18% of the whole class are boys that don't love mathematics. Now we can check that. 0.27 plus 0.18 adds up to 0.45, so that makes sense. And also vertically, 0.55 plus the 0.45 gives us 1 as well. That makes sense. Let's move on. We know that 35% of the girls love maths. So we have 0.55 or 55% of the class. We multiply that by 0.35 or 35%. We find in the whole class, there is 90% of the class that are girls who love mathematics. As a decimal, 0.19. Of course, if 35% love mathematics, that leaves us with 65% of the girls that don't love mathematics. So 0.65 of the original 0.55 gives us 0.36, or we could say that there are 36% of the students in the class who are girls that don't love mathematics. We can check that. We can add them together. 0.19 plus 0.36 equals 0.55, and that holds true. Finally, let's add up our vertical columns. 0.19 plus 0.27 equals 0.46. So that tells me that 46% of the entire cohort love maths. And on the right-hand column, we've got 0.36 plus 0.18 gives us 0.54. Or we could say that 54% of the entire class don't love mathematics. Sad statistics. Finally, let's check this bottom row. 0.46 plus 0.54, or 46%, plus 54% does give us 100%, or decimal is 1. So here we have a two-way table representing the information that's presented in this scenario. Let's try a problem. Let's find the probability that a randomly selected student is a girl if you know they love mathematics. So this is conditional. We're trying to find out what's the chance of selecting a girl if we know they love mathematics. So first of all, the probability of a girl being selected given they love maths is the probability of the girls being selected and that they love mathematics divided by the probability of those students that do love mathematics. Okay, it's the probability of A and B divided by the probability of B alone. So first of all, girls that love maths is 19% or 0.19. And the probability of all students that love maths is 46%, or 0.46. So when I divide those two through, we find that the probability of selecting a girl from the class, and given that they love mathematics, which is a conditional probability, is 0.41 to 2 decimal places, or 41%. Thank you for watching this video on conditional probability. I hope the representation of visual, Venn diagrams, and two-way tables has helped you understand what's happening with conditional probability. If you've enjoyed this video or learned something from it, please like, share, and comment. And don't forget to subscribe. And as always, thanks for watching.